Okay, this session starts. Okay, let's start. And this session is about lattice-based signatures and the elliptic-curve cryptography. And there will be 4 talks in this session. And the first one is angular interval generation, and Chen Nguyen will give the talk.
Okay, thank you for your introductions. Very happy to be here to present to you our unpack the new shuttle generation for post-quantum signatures such as Omega and Quantum. This is a joint work with Elliptic-Curve Cryptography this running. So first of all, I will mention a little bit about the least competition, the least post-quantum cryptography standardizations started in 2017 by an American these well-received competitions have been attracting a lot of new designs in cryptography which are quantum resistant. So in 2022, Quantum and post-quantum signatures based on particle size over lattices has been chosen by me for the future standardization for being fast, having source signatures and having least level securities. All these advantages are supported by a specific structures, which is depending on parameter choices, hard for the implementations. Also in 2022, there was an effort to simplify this design in Quantum, which results in metadata with more freedom in parameter selections, simpler for the implementation and still be as fast as Quantum. However, the trade-off is that the signatures of metadata is about 15% larger than Quantum's, which likely impact the security of metadata. So that's why we have unpacked, born with a mission to make metadata secure as Quantum. So before going into the detail of unpack, I will show you how to size with Quantum and metadata. Their principles is the height and size over lattices. So given a matrix M, a lattice lambda, and a specific basics of lambda, we will call later the secret trapdoor SK. First of all, we will have the matrix M into a random point in the lattice in the underlying vectorial space of the lattice lambda. Then we will find a vector B in lambda when it close to C within the radius gamma. Finally, the signature is actually the difference between C and its close vector B. For the verification, the signature is set if it's more enough and that the hash of the matrix is different from signatures by a vector in the lattice. In practice, we use the discrete Gaussian sampler with the help of a secret trapdoor to solve the problem. The closed vector problem was one of the hard problems in lattices. There are 2 important remarks about the security of these hashing type of lattices. The first one is that this security is related to this closed vector problem, which is hard for anyone who doesn't have the secret trapdoor escape. Secondly, the smaller the discrete Gaussian sampler is, the better the security becomes. So, in order to have a discrete Gaussian, in order to have small discrete Gaussian sampler, either we have to have good discrete Gaussian sampler, which is the work that's presented in the next paper, or we can try to improve the parity of the trapdoor. So in the literature, in this paper, we actually go into this direction of improving the trapdoor. In this literature, good parity trapdoor means short basis of the lattice. There exists a family of lattices on which we know quite well how to generate the source basis. That's the actual lattices, which is using Quantum and metadata. The construction is based on a ring, a special ring. This, for example, this ring is one of the 2 ranges in Quantum, and we also need a large enough palm for the modulus, a large cube. So, we're then interested in small polynomial, which means that a polynomial which is small coefficients. So we obtain the first a small vector in K2. Then we are interested in small solution of these equations. We'll call the answers equation. Thus obtaining the second sort one in the sort vector in K2. Then we generate two large vectors from Q and F and G. Interestingly, the two pairs generate a same lattice called the answers lattice. In other words, the pairs are two bases of these answer lattice. And we'll take the shorter one as the secret key, also the trapdoor, and the longer one as the public key. Now that we have a trapdoor, let's do some discrete Gaussian with it. Starting with a reminder about the Gaussian distributions. So here is the continuous Gaussian distribution of real number, and these are discrete versions on integers number. Finally, we have discrete versions on ring. These two discrete versions of Gaussian distribution are actually sampling unit for something higher dimensional discrete Gaussians in Phantom and Midaka. We will show you later. So finally, we are here with a discrete Gaussian sampler taking the inputs as with a source basis of the lattice lambda, a port C, and we will return a port V in lambda which is close to C. So in general, V is just linear combinations of elements in the basis Sk. Depending on how Sk is represented, we have the claim GPV sampler which initially is by Phantom and the Harvey sampler which is used actually in Midaka. So as you can see here, in K and GPV, Sk can be seen as a matrix of Z of dimension 2 and time to n, while in hybrid sampler is a matrix of K of dimension 2 times 2. Because of this different, in order to sum the contribution is the elements of the basis in V, we need for K and GPV we need to sum discrete Gaussian vectors of dimension 2n on Z. While for Midaka is discrete Gaussian vectors of dimension 2 on K. And in terms of complexities, KGPB actually quadratic. That's why that's the reason why it's not actually used in Phantom, but in variance, the FFO factor will use instead. The Cauchy-Linear complexity of FFOs is obtained by changing the integers metric into binary floating point tree or the Phantom trees will be hard to be implemented with the security. Phantom trees are also the reason why Phantom limited on parameter selections. For example, you can see here we have a tower of ring, and we need to descend these towers. So by dividing the degree n here, the degree n in the polynomial from n to 1. Just by dividing by 2, which means that n is actually a power of 2. So that's the restrictions on parameter selections. If we look at this way, Midaka is more in favor for the implementation. So we might have questions that what's the reason why Phantom designs went that far of introducing this kind of complex structures just to keep the discrete Gaussian sampling unit of that. The answer is related to the security. In fact, the Phantom samplers is smaller than Midaka. As you can see here, the size is different. So as said in previous slides, smaller sampler means better security. For example, here you can see the Midaka is more friendly for forgery attack than Phantom. In order to improve the security, we need to reduce the size of the signatures, or rather the size of the samplers, which is actually related to the norm of the trapdoor measured in the matrix of the sample. So in Midaka case, it means that we need to find improving the security of Midaka means to find a more compatible trapdoor for the hybrid sampler. So to do it formally, we introduce a parity alpha of the trapdoor, which is red here. For example, alpha beta is about 1.17 for trapdoor and 2.04 for beta. More precisely, we define alpha as the ratio between the norm of the trapdoor and the volume of the lattice. Our goal is to minimize alpha to improve the securities of beta. So the first observation is that alpha only depends on FGs, which means the first column of SA, because the second one, the capital F, capital G, are actually small solution of the two equations, which are totally defined by the F and G. And we will not talk about this today. So previous methods suggest sampling F and G from a small discrete portions on Zn centers at 0. Because the information, because the only information we know about F and G from the construction of the actual lattice is as F and G are small polynomial. So with this method, we can actually find F and G such that the trapdoor satisfies this inequality. And for reminding, with this method, we can actually find the trapdoor of parity 1.17 for trapdoor, but we cannot find the trapdoor of such small parity for beta. But with our method, unhack, we can actually find the trapdoor of parity even smaller, the 1.15 for beta. So how we do this? Is that we revise the definition, the norm of the FG of the trapdoor in a hybrid matrix, so that we can find a better sampling method and a more compactable sampling distribution, sampling domain for hybrid sampler. So more precisely, in hybrid matrix, we are not interested in the Zn representation of FG, but the Fourier representation, which means the evaluations of FGs over n root of unities related to k. So for a small space alpha, we transform the problem to finding FGs such that these evaluations signifies this type of inequalities. Geometry speaking, it means that the evaluations stay inside the positive quarter of the annulus, limited by square root of q over alpha and alpha square root of q. Now, in order to generate FG, we will generate the Fourier representation of FGs as n uniformly distributed point in these annulus. However, when we apply the inverse of TFT, we obtain polynomial with real coefficients. In order to correct it, we will route these real coefficients to the closest integers. So we obtain FG in Zn. However, when we reapply the TFT, there is always some evaluation staying out of the initial domain. We understand that this phenomenon is caused by the errors from the routing, from the corresponding routing. So after the analysis of routing, this routing error, our solution is that instead of doing the sampling in the whole domain, we do it in a smaller one. So that in the end, we can have all the evaluations staying in the initial domain with high probability. We will call the success rate. And we can actually control this success rate by choosing the red domain. The question here is, what are achievable alpha from untype? In order to answer that, we study the relation between the parities and the number of reputations, which in fact inverse of the success rate. And we have done this study on all the parameter dimension proposed in Mitaka, in which the first one and the last one are two cases using Python. So here we can see that there's an agreement between our theoretical predictions, which are in continuous line, and the behavioral type in practice, which are triangles. So for thanks to this much, we can actually safely estimate the the achievable alpha given a number of repetitions. For example, for the case 512, we can obtain alpha equal to 1 with less than 4 repetitions. For the case of 512, we can actually obtain alpha equal to 1.15, and for the case dimension 648, we can obtain alpha equal to 1.17. About the performance, compared to Mitaga, we can see that the combination of untyped keys and hybrid assembler can improve a lot of the security, and it has smaller number of repetitions in the key generation. Compared to Funcom, untyped and hybrid gives the same level of security and a smaller number of repetition too. If you look at the 3 last lines, we can see that in fact this combination has the best features of Mitaga and Funcom in terms of security, signing speed, and signature size. And it always has small number of repetition. Furthermore, with the key from untyped, these increased most dimension proposed in Mitaga and hybrid assembler are made secure to be practical. So for all the technical details of the analysis and these parameters, I invite you to read our paper, which is available on ePrint. So before ending, I'll talk a little about the perplexity. The first information is that unpack already integrated in the signature schema as which has been submitted to the Korean postquantum competitions, which are ongoing competitions. And for the future work, we would like to have more optimization in the design of unpack. We concern the circular sampling, the new sampling techniques which has been presented in the best paper this year, and we would like to have a full-fledged implementation of this whole system. This is the end of my presentation. Thank you for your attention.
Any question?
Thanks for your talk. Partially is planned the ones optimization best. Congratulations, result in improvement of sizes.
Sorry, can you repeat your question? You want to improvement in the size of the signatures, which depend on the trapdoor or the function is the central. You can so the 19.
What the size of the signature?
The size of the signatures. Okay.
It's the size depends.
Okay, the size of signatures in this the first combination is smaller than Mitaga because we actually have a smaller alpha. And for Funcom, we have a smaller one, a little bit smaller alpha for the dimension 512. So the signatures are a little bit smaller too. And for Funcom in dimension 1024 is a little bit smaller. And the reason for this size is different in size maybe comes from the sampling.
Question? Okay, I have a question. How do you estimate the entropy of your P? You sample in the
So here the idea is first of all we think that the uniform distribution is actually the one that give Lagrange entropy. That's the first choice. And then we do the analysis of this of the whole process, beginning with this uniform distribution, and we say that this choice is not bad either. And we haven't done any comparison of this uniform distribution with other distributions.
Okay, I see. Because
Yeah.
you run it straight number and then somebody.
We in the paper we actually did not have this analysis in entropy in our paper. What I can say is that we have done a lot of experiment on these generations, and we got a lot of keys from this uniform distribution.
Why do you test on hybrid sample or untrue sample?
So can you repeat the question?
There are two samples,
Yeah.
hybrid sample and untrue sample.
The untrue sample, you mean the KNCDB?
Yes.
Yeah. Okay.
And the previous is 2.05, and the alpha equals to. Yes. And the left is small, the right is large.
Big. That's what in the back.
Yeah. Why do you test on entire class sample?
Because there is a difference between the KN sample and the hybrid sample. So the thing is that in order to have a smaller sample, to have a smaller signature size, we need either we want to improve the samples with actually the work in the best paper, or we try to find a more compatible trapdoor for the sampling, and here we choose the second way. So we accept we want to keep the hybrid sampler because of its simplicity, so that we try to find a more compatible trapdoor for this hybrid sampling. And now with the untype, we can obtain untype equal to 1.15 for the hybrid sampling. I don't know if that answers your questions.
Simplicity is what?
Sorry? Simplicity.
Yes.
Simplicity is that we because hybrid sampler is simple. It's simple to implement. Simple.
Thanks. And the second talk is G plus G, Biot-Jamir lattice signature based on both the Gaussians and let's learn.
Alright, so thanks for the introduction. So yes, I'm Pascal, I'm going to talk about G signature. So what do we do in this paper? Oh, okay. So in this paper, this paper is about the other main strategy for building lattice-based signatures, which is Biot-Jamir lattice-based signatures, or also called relationship signatures. And so the main challenge in relationship signature is to prove the zero-knowledge property, the underlying identification scheme, or with to prove that the signature does not reveal anything about the secret. So far, there are mainly two techniques to guarantee the security of the scheme. So the first technique is rejection sampling, which is used, for instance, by Elliptic-Curve. So it's a good technique that relies on aborting the signature protocol many times until we get some distribution that is independent of the key, and then we get small signatures. And then we have also another technique that avoids aborts, which is noise splitting. So this is, for instance, used recently by Asiacrypt, but then the cost is that the signature is much larger. So in this paper, what we provide is a new technique for providing security, and the technique is actually Gaussian convolutions, and we don't rely either on rejection sampling or on noise splitting. So in the end, what we get is a signature that is as small as the best signatures based on rejection sampling, and we don't rely on it. So just a quick word on why we care about aborts. So there are actually this year at Crypto, we proved, another team also proved that there were actually minor flaws in the oldest proofs of rejection-based signatures because of like kind of subtlety that appears when you put in the ROM or QROM these things because of the aborts. So it's one reason to avoid it. And also aborts make advanced implications, for instance, special signature a bit complex because if you have multiple signers, and as soon as one has to abort, it's basically. So that's one of the mitigations. All right, so if you don't know anything about the UHFT signatures, stay with me because I'm going to spend most of it explaining what was done before, and then at the end of the talk, I will explain GPC. So UHFT signatures are basically adaptation of Schnorr signature, or Schnorr identification protocol to a lattice system. So it was introduced by UHFT in 2009. And so the main strategy is to just transfer the Schnorr's protocol, which is based on this pattern, to the lattice system by relying on lattice problems. So for instance, SIS or LWE or variants of it. And so for this talk, you can just think of these problems as the following problems. So you are given some matrix A, which is just a large matrix, some target matrix, which is A times S, for some small secret matrix S. And so the problem is to recover the solution S. So it's basically the same as discrete log, except that now you have an additional constraint, which is that the secret is small. All right, so let's have a look at how the underlying identification protocol works. So the prover is basically giving the secret key, so the small S. And the verifier is giving the public parameters, which are the matrix A, the large matrix A. So orange is small, blue is large, and the target T, which is A times S. And so how does the protocol work? Simply, first the prover samples some small value Y, which it commits by providing A times Y, but Q. So far I'm working with Q. And then the verifier replies with some binary challenge, which is a highly completed string. And at the end, the prover replies with some value which is Y plus SC mod Q. And so verification does the following. So first check that C is small, so it's supposed to be small. And that's this equation holds, so AZ W plus TC mod Q. All right, so this is the underlying protocol, sigma protocol. And so for this talk, so there is actually a lot of flexibility in the choice of what I mean by Y small in practice, but for this talk, you can think of it as Y for now just being sampled from a Gaussian distribution. This is a very common choice. All right, so how do you get the signatures from this? You just apply FetchME. So you just remove the interaction by sampling C as being the output of a hash function model as a random oracle applied to the public information that's available to the verifiers. So your signature is basically the WCZ. And actually, if you check a bit, you can see that W is equal to AZ minus TC mod Q. So you can tune a bit, change a bit the verification algorithm such that you just need to read C and D, and then your signature is kind of small because C and D are small. So that's it. So I'm not going to talk about signatures anymore. I'm just going to focus on the underlying notification. All right. So what do we want from the notification protocol? We want three things. So we want completeness and soundness. So completeness basically it works if everyone is an S. So just follow by inspection of the terms. So in particular, Z is small because it's a sum of small things, Y and S, C are small. Soundness, I'm not going to go into the detail of it because the way we do it for GPT is basically the way it was done before. So it just flows from the RMS of SIS, LWE, or the variance of it. And so the focus of this talk is going to be about zero knowledge. So how do we get zero knowledge? So what is zero knowledge first? So we need this verifier zero knowledge, which basically says that the transcript that you get from interacting with the honest prover and with as an honest verifier doesn't really do anything about the underlying secret. So how is it translated in a security definition? Just there exists some real-time simulator that takes as input the public information that is available to the verifier, so A, T, and C, and outputs a transcript, so WCs. And so what do we want? We just want that the transcript produced by the simulator is basically statistically close to the actual transcript you get from interacting with the prover. So there are different ways of defining it, either with the statistical distance or with the rate divergence. I'm not going to insist on that, but we do both. All right, so what's the simulation strategy? So again, you want to construct a polynomial simulator that takes the public information A, C, and C and return the transcript. So C is part of the input, so you don't want to produce C. So the question is how do you produce W and Z? So again, if you remember, the W is bound to be AZ minus system of Q because of the second verification equation. And then the question is just how do you sample Z? So Z, you want to sample Z that has a proper distribution. You want to do it without the secret because you don't know it. So, okay, so let's check with the protocol. So in the real protocol, Z is Y versus C. And so Y is Gaussian distribution center with 0. So Y versus C is just the same distribution, but just shifted by S and C. All right, so we want to sample from this distribution, which is the Gaussian distribution with center SMC. So the question is how do we do it? So it doesn't seem completely straightforward to do it, and the reason it's not straightforward is that this protocol is actually not secure. At least not in general. So, okay, let's see how to make it secure. So the question is, the problem is how to make sure that you can sample publicly from the distribution of Z, which is Y versus C, without knowing the secret. Yes. So there are two solutions that are known in the literature, which are Richardson sampling and noise flooding, which work as follows. So first, solution one, which is noise flooding, is just to choose Y such that basically remains unchanged when you shift it by S times C. So the distribution of the green curve and the blue curve are basically the same. So how do you do that? You take Y, which is much larger than SC, but still you need Y to be small in the protocol, so you need to take Q even larger, and then it's relatively inefficient. And so basically what happens is the following. So you take very flat portions, and then they are kind of looking alike, and then sampling from this basically sampling from Y, which can be done publicly. So that's noise flooding. Then the second solution is rejection sampling. And so how does rejection sampling work? Simply you want to make the distribution of Z, which is now for now dependent on SC, independent of it, and you do that by rejecting some target distribution. So let's say you want to reject the distribution of Z to the distribution of Y, which is publicly sampleable and key level. So okay, so how do we do that? Simply you can see that sampling some Z is just sampling the random points under the blue curve and outputting so in the area under the blue curve and outputting its axis. This is exactly the distribution of Z. So the same thing, you could do the same thing with now the scale curve, which is the distribution of Z times some scaling factor M. So again, sampling an element of Z is just sampling from a point under the red curve and outputting its axis. Still exactly the same distribution. So the key idea for rejection sampling is just that you're going to do that, but then if you fall into the red area here, you're just going to reject. So basically you reject sample Z based on the probability between the red curve and the difference between the red curve and the green curve. So for this to work, you need M to be large enough such that the red curve is above the curve. And so basically, if you do that, what happens is that you sample from Z, but the distribution of the output condition of not being an abort is the distribution of the green curve. And then you get something that is dependent of SC because the green curve is SC. And so the expected number of time you're going to abort is basically the area of this red zone in which you abort. It's basically. So this is rejection sampling, basically for rejection sampling. So as you can see, there are choices for the description of Y and Z that makes you reject more or less. And so basically, if you take Y and Z that follows currently spread motion, then the scaling factor can be small because they are kind of looking like already. It's the same as this one spreading. But if you want to take Y and Z smaller, so the motions are more concentrated, then you can see that the scaling factor is going to increase very fast. So you're going to reject a lot. Still have flexibility. All right, so this was for the basic strategy for signatures. So now there is another idea that has been used in the literature, which was introduced by Elliptic-Curve in 2013, which is to tweak a bit the way the scheme works, such that you get a much better rejection scheme. So the idea is to tweak the key generation algorithm. So now instead of working over ZQ, I'm going to work over Z2Q. And so the key gen is going to be changed as follows. So now instead of just something A, like a large matrix A and a small matrix S, I'm going to choose them such that A times S is equal to specifically Q times the identity equal to Q. So it's a very specific target Z. And so the verifier key is just A now, the target is already it's Q times the identity. And so besides that, the protocol remains basically the same, except for 2Q, so you still sample a small vector required, you commit to it like from 2. The verifier set to some challenge, which is a binary string, 914. And the thing is that the particularity of this scheme is that now, because of the new key gen, what you can do is provide two different responses as the last message. So you can either send for Z Y plus C or Y minus C. The thing is that it doesn't change anything. It's both response to satisfy verification. So I'm going to explain that later. But so why does this help for predicting something? The thing is that now the distribution of Z is no longer the shifted distribution of Y, which is this binary motion. And so as you can see in this drawing, it's more spread, it's symmetric. So actually, if you want to do rejection something to Y now, it's much easier because the scaling factor is going to be much smaller. So basically, you have a choice. Either you keep the same parameters and then reject less, or you can reduce the parameters and then get smaller symmetries and reject as much as you want. So that's the main idea, but not really important for what I mean. Okay, so let's go back to why does this new key gen works. Why do we have two options for the response to the challenge? So okay, so we want that. So what we have is that A times S is equal to Q times the identity of 2Q. And so what it implies is basically that 2 times A times S is 0 over 2Q. 2 times 2 is 0. All right, so let's check why the verification pass. So first, there is one option for the response, which is Y plus S times C. And so clearly, if you use Y plus S times C as the response, then it passes verification. So in both cases, it will be small, Y, S, and C are small. And then the second equation is satisfied because basically A times Y is W, and A times S is Q, so we get W plus Q. Okay, so this was the easier part, but the other one is easy as well. And so the main observation that we do, and that is at the center of actually G plus T is the following. So the thing is that Y minus SC is basically Y plus SC minus 2 times S. So part of the thing extremely complicated, but actually if you understand this, basically gets why we can do better than. Okay, so then what happens is that you have A times Y minus SC is just this equation. And the thing is that because of the key gen, the last term is 0. Because 2 times A times S is 0. So again, we pass verification because in the end the minus 2SC terms will cancel out, and then you get the same thing that if you are using Y plus C. All right, so what's the idea? Now to get G plus T. The thing is that it doesn't matter that I chose C as the last component of this equation. First, you need C at the beginning for the plus A times SC. You need to make the same thing as if you were using A Y plus C. But the last C doesn't matter. The only thing that matters is that last term is in theory. Because what you want is that this term to get cancelled out multiplied by A. So the thing is that the second verification equation will still pass even if you choose y versus c plus 2 times s times h or any h in this situation. So just because 2 times a times s is equal to that's it. So okay, so what's the idea for G plus G? Exploit that. Just choose more options for h. Just not minus 2 times s here that was done before in this. So again, the idea is that any z of the form y equals sc plus 2 times sh will pass verification, at least we pass equation 2. But still we need to pass also equation 1, so we need this form. So how do we make this form? Just choose h to this form. So this is actually what we do in the system. So the reason for G plus G is Gaussian, and the Gaussian that we have are the Gaussian for y and the Gaussian for h. So we both take them Gaussian, so it's like that. All right, so how do we pick them now? Because we still have the secure system. So if you remember, the point of reducing something was to make distribution of z completely sampleable. So what's the distribution of z in this scheme? It's y plus s times c plus 2 times s times h. So it's still centered in s times c. So this was the problem at the beginning, it's still fine for us now. So how do we make the distribution of z completely sampleable? First, we want to erase the fact that it's centered in SC. And so how can we do that? Just take h, which is centered in minus c over 2. So why do we do that? If we do that, 2 times s times h, it's now a Gaussian distribution as well, which is now centered in minus sc, and then the centers become 0 for c. Just on side of the s, the plus sc there. Okay, so are we done? No. So the thing is that we not only want the distribution to be independent to be centered on 0, we want it to be publicly sampleable. And so being publicly sampleable means that it does not depend on discretity. And the thing is that here it's still dependent on discretity because even though we have cancelled the S term, so it's now centered on 0, the covariance matrix of 2 times S times H is actually dependent on S discretity. So we need to cancel that out as well to make actually Z publicly sampleable. So how do we do that? As I said at the beginning, I told you let's think about y as being Gaussian vector, but actually there is flexibility in the way y is defined. So why don't we just pick y Gaussian so that the covariance matrix is the following, and then the minus 4 times sigma prime squared times s transpose will cancel out the other covariance term that appears. So if we do that, then the sum y plus sc plus 2 times s times h just follows the Gaussian distribution centered on 0 with public standard deviation z. And that's it. So this is public. So okay, so that's basically the main idea for G plus G. So here I'm cheating a bit because I'm talking about continuous Gaussians. So it's slightly simpler. So this is basically what happens. You're basically solving two Gaussians, one with smaller dimension, the other one with cube. And then in the end, what you get is spherical Gaussian distributions centered on 0. So again, I'm cheating a bit because I'm talking about the continuous case here. We are actually interested in the discrete case, but if you follow the first of this one from Thomas, basically what happens is that the discrete case works well if you have good enough standard deviations. And so again, there is actually, we don't even need to do anything in the paper to do that because there are actually name lists provided by the previous paper that tell exactly what we want. And so in the discrete case, it works as well. All right, so let's just finish with this. So what's the G plus G protocol, the identification protocol? It's basically exactly what I just said. So you sample the same gen as for the value system, so A times S should have the picture. You sample Y with the covariance matrix which depends on the discretity. You commit to Y, you get a change. You sample H from this specific Gaussian with center minus C over 2, and then multiply with this value. And the verification is the same as before. So why does it work? So completeness and soundness. So completeness I already did, I just explained a precisely by before. Z is small because everything is small. Soundness is the same as before, and so zero knowledge was the simulator now. Simulator is completely straightforward. You just sample Z from the actual distribution that we made everything so that Z was equal to some so it's this motion. And W, same as before, you make it by verification, so AZ minus 2C. So that's it. Alright, so let me continue. So just to give you some ideas of the performances. So this is a comparison with state-of-the-art signatures based on Chachamia without or study techniques for signatures. So just for comparison, I gave the Raccoon and Dilithium. So Raccoon is a signature based on flooding, so the comparison is not super fair, but of course it's larger, just the cost of flooding. Dilithium is just for comparison because it's the new standard, but it's also not made the most compact because it's using Asiacrypt and Ocean variables. So the actual fair comparison is the two lines TFPS 22 and 810, which are recent proposals based on hyperballs, which is the most efficient distribution for distribution. And so with aborts and using either linear or binary setting. And so as you can see, G plus G is actually comparable in terms of performances with them. It's actually better for signature size as soon as you push the secret parameter further than just one. For public key, we are slightly worse, even if the gap tightens if you get larger secret parameters, but still we are in the same order. So, alright, so that's it. So there is more in the papers with all this stuff. And there are one problems that are quite interesting, in particular on signatures from this. It's not straightforward actually. And yeah, so that's it.
Thanks for your method. In KJ, you generate small s such that as equals Q times IK. So it seems to me that this is an inhomogeneous version of this. How can you do this?
So basically, so the keygen is basically the same as this. So we don't invent the keygen. So basically, the keygen like you set the matrix. So the matrix A that the one is actually not a uniform matrix, that's just a structural matrix. One part uniform, but the rest is uniform. And so it's like this is relatively easy if you it's relatively easy.
So you first sample S and you compute A times S? But I mean, the Q times IK is fixed. So it seems to me that this is an instance of inhomogeneous space. Sorry, I mean, it seems to me that the generator S, such as AS equals QIK, is not that easy.
I mean, it's first one before it's
Yes, thank you.
Yeah, so yeah, as you mentioned, the case that we have rejection samples, honestly, two signatures together, there is no guarantee that the aggregated amount of samples is not perfect. So here you have a similar constant that we need this estimate small. So how you can basically, because if you independently sample two estimates small by two different functions, but add them together, how do you still guarantee that this is small? With this seems to be similar problem that you have in rejection sampling. Yeah, so yeah, so the reason I mentioned it, so I mentioned the motivation, so it seems that we're moving about the help. But the thing is that this doesn't seem straightforward at all how we get that from. And actually we spoke about it so far. And so one of the reasons is that the white parts depend on the actual state. And so it's not clear about this that. Okay, so it's definitely totally open to it's a very challenging question. So one thing we make extension to Asiacrypt? Why we cannot say this? Like, so there are all these recent works on like there have been very important progress in the last years for the Asiacrypt. So I think so yeah, like the kind of similarity used for
our its neighbors and within the Thank you so much for the introduction. The slides are ready. Great, thanks again. Is it? Yeah, so I'm going to be presenting work for here it's a lattice-based elliptic-curve set track, and the title is sort of looks like nothing to do with it. But at least convince you that there's something going on in this work related to at least elliptic-curve. So in this talk, I'm interested in looking at specific type of consecutive images. In particular, I'm interested in finding these ones that are patterned among this whole list of there's probably hundreds of reasons why one might be interested in finding these numbers. But one thing that looks particularly striking is if you look at their factorization. See, all numbers that are in gray, they have large prime factors. Even one is prime itself, one that ends in 5, so just a prime factor. Now, these ones that are highlighted in purple, these kind of break the range, and the largest prime factor is very good. Now, in setting of isolationally based crypto, having these sorts of numbers, which is small prime factors, yield better isolationally computations. Isolationally computations are much faster when the prime degree is relatively small. So in some sense, we're interested in finding these, but we could track this. So to formalize this a little bit, I'm going to say that pair of consecutive images are +1, B smooth twins, if their products aren't about in the sense that each prime factor of this product is a close fit. I mean, if their product is B smooth, then naturally the numbers themselves are good. Here's another example that I always like to have in mind. These are 7 smooth twins. The largest prime factor in their product is 7. And whenever I talk about these integers to people outside the research community, I always seem to have this. What I think is a little bit surprising is if you fix a smoothness bound B, then the set of B smooth twins is 5. This is kind of contrary to some other results that say that if you think about it from the prime number setting, we conjecture that they're infinitely many twin primes. And in this setting is the exact opposite. We have an actual proven theorem that says that the set of B smooth twins is 5. And we can actually count all of B smooth twins. And in particular, this example 7 smooth twin that I have up here is the largest among all 23 7 smooth twins that we have. Now I go up to 113. This smoothness bound is the largest smoothness bound whereby we know the exact number. Anything beyond this, we can only give like a lower bound. And for instance, for something like B equals 200, we have this lower bound, but we can't be sure that this is the exact number of these. Actually, the example from the previous slide is the largest 200 smooth twin that we know. As I mentioned, there's interest for these sort of integers in Asiacrypt-based cryptography, but there's also other applications in computation. From a cryptographic point of view, this is the most. So going into this work, we kind of had like one big question, and that question is, can we find the largest piece of this? And we identified 3 algorithms which we thought could best answer this. We have the one on the left-hand side based on the Pell equations. This is like the most traditional way of finding these piece methods. And it's actually the only way we know that we can enumerate all of them. Now, the one on the right-hand side, based on the PT sim, this is particularly good for finding cryptographic size twins, but doesn't necessarily answer our question of finding the largest piece twins. In some sense, reducing the smoothness bound as small as possible. And then we have this one in the middle, for the CHM algorithm, which is kind of been overlooked for the past 10 or so years. Not really given much treatment. So we decided to revisit this algorithm to find the record size. And then later on, I'm going to be discussing how we apply them to something like a ski set. So this is how I'm going to outline this presentation. I'm going to start by going over the CHM algorithm. Then I'm going to be talking about how twin integers actually apply, so it's looking at protocols. And to wrap things up, I'm going to talk about the actual speed-up parameters that we found using the CHM algorithm, plus some other things. So the CHM algorithm is an algorithm that was proposed in 2012 by Conway, Holstrom, and Foreign. That doesn't do as good a job as we want to find all of the base motifs, but does a pretty good job. And in particular, it finds almost all of the base motifs. And the idea is the following. We're going to start with an initial set of these twins, which I'm just going to write them as the numbers on the left hand side. So this is the 1 up to 3 minus 1. Now what we're going to do is we're going to take each pair, R and S in this big set, and do this big, sort of big computation. Do R divided by R plus 1 times S plus 1 divided by S. And we reduce this down as much as possible so we get T prime. And what one can show is that if this T prime is equal to T plus 1, then we could get reasonable. So what we're going to do is we're going to create a new set that we call S1 to be exactly what we have in S0 plus these new solutions that we get from doing this implementation. Now we're going to repeat this process, replacing the S0 that we have at the start with S1, doing all pairs R and S and S1, doing this computation, finding the ones that are new reasonable twins, and adding to sets. We're going to continually repeat this over and over again. And as I said, because the set of base smooth twins is finite, at some point this procedure must stop. And when it does, then we just stop. And we can reformulate this CHM equation into something equivalent. You can just solve, if you solve for T, then you say T prime equals T plus 1, and you get something like this. And so doing this computation to get T prime equals T plus 1 is the same as checking that this number here. So I think it's good to see this in action. So I'm going to show you an example of this with B equals 5, and hopefully try to find either almost all or all 5 solutions. So the initial set is S nodes, all numbers from 1 to 4, which represent the B-smooth twin, say 1, 2, 2, 3, 3, 4, 5. Now we're going to go through each RNS in this set and see when this computation gives us something new. So if you are quick with your mental maths, you can see that there's 6 of these computations that we need to do. 3 of them either don't give us anything new or just don't give us smooth twins. But the other 3 do. And in particular, when you do it with I equals 2 and S equals 3, then you get the smooth twin 8 and 9, and then 5 and 6 and 15. So we're going to add these numbers 5, 8, and 15 into our big set, and we have S1 comprising of all these numbers. We repeat this. The second iteration, we get 2 smooth twins. I think we get 9 and 10, and 24 and 25, which we knew. The third iteration, we get 80 and 81. Now the fourth iteration doesn't give us anything new. S4 is equal to S3, so we stop here. Nothing will be. And this is by coincidence. This is actually all 10 bi-smooth twins from the table I had on the previous slides. Now this is a bit of a coincidence. In general, you can't expect to find all bi-smooth twins from this sort of procedure. One example of this is if you just go to the next prime up, B equals 7, you actually find all of them apart from 1. Now, if you guys are not half asleep or paying attention to my slides, you might have a guess at which one is missing. The one that's missing is this 7 smooth twin that I showed you. Now, this starts to be like a bit of an anomaly because for at least B up to 41 greater than 11, this procedure actually finds all these smooth twins. But for all B greater than 41, then at least conjecturally, we find almost all. In particular, one example, the original authors of this algorithm ran this for B equals 100, but at the time we knew exactly how many unsmooth twins there were, and they found all of them except for 4. And they also ran it for B equals 200, finding this number of B smooth twins, and their computation took about 2 weeks. So we revisit this algorithm and give an optimized implementation in such a way that we can run it much, much faster. And in particular, we run this B equals 200 for our code, and instead of taking 2 weeks, it only took 7 minutes, which was kind of fun to figure out once we realized that it was really that fast. Number of ways that we kind of did this, we kind of made use of that equivalence that I showed you in one of the previous slides to, I think, probably do the computation a little bit faster. We also kind of incorporated some parameterization, which made it possible. If we can run B equals 200 much faster, then we can expect to run it for a larger B. And in particular, we ran it fully for B equals 500. Found this number of B smooth twins, and this is the largest one that we. And this is a plot of all of the largest B smooth twins going up from the smallest all the way up to 500. Now, if we want to have cryptographic sized twins, we kind of need at least 256 bits. Now, if we want to apply something like this to find that 256 bit twins, we have to run it for at least like 5,000. And that's just infeasible given the implementation that we do. But we actually did run it, the algorithm for larger B. And what we did was ran the CHM algorithm, but did not check all pairs RNS in this. We restrict ourselves to only checking certain number or certain sized RNS. And then we give like a few ways of doing this. I'm going to present just two of them here. One thing you can notice is that if S is like much bigger than R, then the likelihood of your computation giving you something new is very high. So this is what we call the global K. We're going to fix some K and only check the S which are within this interval, greater than R and most K. The other optimization that we have with constant range. So instead of checking R and S in like some interval, we ordered this set SI and only check the R and S that are some successive and some range larger than R within this set. Here's some like numbers of how these optimizations perform. You can see with B equals 200, 300, if we ran the full algorithm, it took us about an hour to run. But with these optimizations, we can run it for at least like 5 minutes, and in some sense, 60 seconds. And we still get like a large portion of it. So we did run this for some large B, and one example that we did was running for B equals 700. So the goal of that run was to record the largest ones. As we'll see later, this is actually. So now I'm going to go into the isolationary-based protocols. And here, the actual thing that we want is we want to find primes P such that P plus 1 and P minus 1 are as smooth as we possibly can. Few cryptosystems require this sort of setup. One is it was originally P-side that proposed these sort of things, but it's now broken given the SSH packs. Another one is the C-side. And the idea is that we're going to work with super single elliptic curves with either P minus 1 squared points or P plus 1 squared points. And thus we can kind of keep our isolation computation fraction. Now, you can think of these sort of primes like a special case of the principal. And in particular, if you have a smooth twin R and R plus 1, and you take their sum, 2R plus 1, then you get exactly what we have over here, if it is a prime. And if you look at the factorizations of P minus 1 and P plus 1, they contain R and R. Now, this makes all of P squared minus 1 smooth, which is kind of the optimal of what we would like. But in isolationary-based cryptosystems, we don't really need all of this to be smooth. And in fact, we only really need like some large factor of P squared minus 1. And if I kind of translate ourselves to B side, pre all the SI and the H attacks, what they required there was a prime P whereby the factorizations of P minus 1 and P plus 1 have a large smooth factor that are roughly the same size. And the other factors, they can be rough. They don't need to be because we're not needing them. So now let's go into ski sign, which is kind of the main focus of this work. Ski sign is an identification protocol, which is turned into a signature scheme verification. And the idea is that the identity is going to prove knowledge of the CPP by solving some isogeny. Generally, this is quite hard, but with the specific setup that we're going to have over here, this is going to be quite hard. And the way we're going to do this, we have a public elliptic curve on the top left, E naughts. We have a public key private key pair, which is essentially an isogeny super single elliptic curve. Then we have the identification protocol, which produces a commitment isogeny. Then we have the challenge isogeny on the bottom. And then the task of the owner of the public key private key pair is to solve the isogeny problem between EA and E. That is one very natural way of solving this isogeny problem, which is to just take the composition of all these together. But that obviously reveals your CPP. So sometimes we need to compute a new isogeny. And we can compute this isogeny given this isotropy plus some endomorphism knowledge of A, which the owner can compute because he knows all of the aspects. And the challenger only really knows the isotopies which are involved. So in terms of the prime, what specifically do we need? We currently, the state of the art requires a prime that sort of p squared minus 1 decomposes into its smooth factors. We have a power of 2 times by some smooth factor t. This power of 2, we want it to be as large as possible, and we want to reduce the smoothness bound of t as small as we possibly can to make our isotope. And the idea is that the t is going to be used to compute the commitment and the challenge isotopies. And the power of 2 is used to compute the verification isotope. This square b divided by f is kind of a rough cost metric of how well the designing is going to perform. It's in some sense like a worst case bound, which we use in this one. And because the computing isotopies are degree 2 is very, very fast, this makes the verification fast at the expense of signing getting fast. Now, in terms of the prime that we need for this security 1, we need a prime of about 256 bits. And in this way, we want to define larger primes as well. So for this 3, we want 384-bit primes, and this 5, we want 5. And prior to this work, only 256-bit primes. So this was the state of the art prior to Alpha, and it performed quite nicely. Yeah, so the idea to define this, the main goal was to use some sort of extended Euclidean algorithm. You force some power 2, you force some power 3 into p plus 1, p minus 1. And then some other small factors as well. And you use the XGCD to recover the integral. Now, a small point, this cost metric square b divided by f is not as small as we would ideally like it to be, but it actually performs the best because we have this large power. That's something that we're going to kind of touch on with us. So now going into the primes that we find, and the idea is that we're going to use this CHM algorithm to find ski-sign primes. As I said earlier, we can't find 256-bit twins from this approach, or we can kind of boost them up from polynomials. In particular, we use this polynomial 2x to the n minus 1 to boost them. If you look at the factorization of this polynomial squared minus 1, at least for all n, it contains x to the n and x minus 1. And for even n, you also have x plus 1. Just because of our side. And so the approach is that we start with a CHF twin, that we'll write this way. We choose an n and evaluate this this polynomial at the CHF twin R. Now we compute the smooth factor of p squared minus 1 and decompose it into power 2. And we keep it or record it if it's a prime, and we have this great size requirement for t, and the Scotch metric is a small p. Now, because we're incorporating the CHM twin, we have like at least a guaranteed amount of smoothness from p squared 1. And in particular, for a particular n, we have a guaranteed smoothness of this size, p squared 1 plus 1 there. Now, depending on the power 2, you get plus the n that you choose. This might not necessarily be enough, and you might have some more factors that you need to have. And you can just repeat this as much as you can to find it. And this comes with a. So which end should we choose? That's an important question. If you choose n equals 2, then the amount of guarantees is e to the 3/2, which is quite a lot. And in particular, it's as much as we need for something like this. So we don't necessarily need anything more from the other. The downside for this is that we need twins are to be about 128 bits. So this number is quite small, so we're not going to have lots of 128 bits. N equals 3 is a little bit of a trade-off. We get a small amount of guaranteed smoothness, but now we only need to find 85 bits. And we have a little bit more of those, but we might hope so. For n equals 4, obviously we get something smaller, but we hope to find more 64-bit twins to evaluate and then find primes. And then finally, for n equals 6, the factorization of p squared minus 1 decomposes into lots of small degree factors. So while the amount of guaranteed smoothness is quite small, we can hope to find smooth factors from the other factors and then use that up to give us the prime rule. But this comes at a cost. For finding two particular primes, we need to find 8 or 3-bit prime. There we don't really have it, just because of the size. And you might think, maybe we can try other n, maybe n equals 5, I kind of skipped over that. But the factorization of p squared minus 1 for that n, instead of factorizing into small degree factors, has like one irreducible factor. So then the probability of us finding enough smoothness from p squared minus 1 to apply to something like these is not. And this is kind of just a picture to show that we have like lots of 64-bit twins from our p equals 547 computation, maybe not as much of the 43-bit twins, and still quite a lot of the 85. So we want to do more search within that sort. So to showcase the results, these are the 256-bit primes we found, and we use n equals 2, 3, 4 to find these primes. The best prime that we found was this prime. The power of 2 is 59. And the smoothest bound of p squared minus 1 is this 470, which is, if you remember from the slide earlier, it's a lot smaller than 3000. And with this, we can probably try to do some sort of comparison. One thing we can notice is that the rough cost metric is a lot smaller. In fact, it's the smallest that we know of at 0.45. So we can do like some estimations of how much faster and how much slower the signing verification is going to be. We did like some rough analysis to show that it could be between 30 and 50% faster at the expense of a slightly slower verification, 31%. And when I say 31% slower, this is still really good because we just use it. But okay, whilst I've mentioned this sort of comparison, these are kind of rough, and the only real way to get a true comparison is to implement this concretely and see how it runs in practice, which is how to scope it. Now let's showcase the 384-bit primes that we found. And we use n equals 3, 4, and 6 to find these primes. Here's one example with n equals 4 that we found. Here's another example with n equals 6. And lastly, the 5 and 12-bit primes that we found. We use n equals 4 and n equals 6 to find these primes. This is one that we found with n equals 6, and this is another one. And here's like a table that showcases all the primes that we found.
So to summarize, I kind of want to take us back to the start where I kind of proposed this question that we wanted to try and answer. Can we find the largest Beechman twins? And in some sense, yes, yes, we did answer this question, but we can only really go up to 120 if it's not something that's suitable for cryptography. And like twins on their own. But what we can do is we can find C-sign parameters from this by boosting or what I might use powerlifting Asiacrypt defined. And we need to find the first parameter sets the target, the highest security levels. These are 384 parameters. And just finally, to kind of extend this question that we asked at the start, a kind of a nice open question that does require some novelty to answers. Can we at least find these cryptographic cycles that have the smallest possibility? This probably requires some few algorithms. Tuition. Any question?
Thank you for your talk. In your paper, you had a generalization of CHM algorithm by using quadratic polynomial. So is that possible if you use several polynomials then to cover all like these trees? So because one, if you use one, someone will miss, right?
Yeah, so that generalization I didn't present in the talk was find Beechman twins from, let's say, a irreducible quadratic polynomial. In particular, the one that applies to finding Beechman twins is the one where the polynomial is something like x times x plus. So if you apply it to some other polynomial, irreducible or could be reducible, but then you can't expect to find Beechman twins from that. So you can't. The only way you could possibly do that is if the polynomial itself factorizes like the polynomial x times x plus 1, what you would find Beechman twins. So in that sense, you would find if the polynomial is something like x times x plus 8, you would find not necessarily twins, but you would find B-smooth values of x and x plus 8. Okay. Which, at least if those numbers divide A, then they give us B-smooth twins, but it doesn't really gain us too much from just like doing x times x plus 1 to find B-smooth twins at least. Maybe they have some other application which maybe you know. Thank you.
Thanks for your talk. So I just want to check some details about algorithms. So how to decide using CHI?
How to decide the end?
Yeah, how to decide it? Yeah. So is there any rules for that?
Is there sorry?
Any rules for the choose of the end?
Any what, sorry?
Rules.
Rules?
Yeah.
Not really. You at least want it to be small so that the amount of guaranteed smoothness is still quite high. Yeah, there's no particular rule, it's just like these are the ends that particularly work well.
Everyone, thanks for the talk. This is a question. Have you considered using other polynomials instead of the p-squared?
Good question. So in my PhD thesis, I extended this a little bit to cover more or less all polynomials whereby the amount of guaranteed smoothness is at least non-trivial. When I say non-trivial, it's bigger than p. If I go to the previous slide. this amount of guarantee smoothness is non-trivial. You can only really, in general, we only really can expect most factor of P. And this is just a little bit more. And in my PhD thesis, I extended it to polynomials where you still have this property and you can categorize it in.
Okay, thanks. This session is non-interactive commitment from non-transitive group action. And Giselle Dalcondo to the talk. Thanks. Okay, I'm sorry to disappoint you, but this is not talk about lattices or about group actions. Thanks for listening. Okay. Okay. This is a work joined with Simple and Jenny and Edith. And we will talk about commitment based on transitive action. We start recording what the action is. We have an X set, G group, and star G times X into X. And we call this triangle a group action if the star is compatible with the group actions. So we want that the mutual element of the group E acts like a mutual element of the action. And the product of the group must distribute well with respect to star. So we have this distributed. Okay, to build the cryptography, we want that our action must be effective. And this means that there must exist probabilistic Orion times algorithms for our objects. So we want to do quality tests efficiently for X and G. We want to make products in versions in G, and of course compute star efficiently. Sometimes we want that our group function is deep observable. This means that given X and Y in X, it must be hard to tell whether there exists an element of the group G sending one into the other, sending X into Y. Then our main assumption is the one-wayness in the action. Even X and Y linked like a G, must be hard to find such a G. In the literature, there are many constructions of these objects. There exist deep changes, Sigma protocols, many other things. In this talk, we will talk about mainly non-abelian actions, even if these constructions or our construction also. Okay, let's recall what transitive means. On the left, we have a transitive group action, and this fact implies that given any 2 points in X, there exists a G sending the first point. On the right, we have a non-transitive action. This means that X is there is a partition X, 2 orbits, and if we pick 2 points inside the same orbit, there exists a G. But if we pick 2 points into distinct orbits, such a G doesn't exist. In cryptography, we use mainly transitive action, like CSI or
Even if recently also non-transitive ones, in particular, the one behind the new signatures, less, but they we usually restrict the action into one orbit, so making the action intransitive by itself. Okay, since we talk about commitment, let's see what it is. We have two vectors, a sender and a receiver, and a sender wants to commit to a value B. So there is the commit phase where the sender puts value B in the box of it and sends a box to the receiver. Later in time, there is the opening phase where the sender sends value B and the receiver that inside the box of the browser actually. A commitment must be binding. This means that the sender can't change the actors of the box, and hiding. So because box must not give any information about the The state of the art for the commitment actions is from two papers. There's one from the 90s, and the second one is more recent. We have public parameters given by a group action, and there is a set of phase where the receiver picks at random an element G from the group, an element X0 from the set X, and computes X1 as G star X0. And a proof by proving that X1 and X0 are linked by he sends this stuff to the receiver that checks. Then there is the commit phase where the sender picks a sum from H and commits to B, computing H star XB. In the commit phase, he sends B and H such that the receiver can check that the commitment is actually H times it. So we have two issues here. The first one is that the proof I can be huge, but it is almost a signature. See it like a signature. And the second bigger problem is that there is an interaction before the phase. It's a set of phase where the sender cannot commit before receiving some stuff. And our goal is to remove this interaction. Okay, our first attempt involves a trusted party. We have public parameters given by a group action, and the trusted party gives two elements, X0 and X1 in different points. The commit is as before. We pick a random G from the group and commits computing G star XD. The opening, as usual, is giving B and G to the receiver, such that it checks that it's C. Okay, this commitment actually works, but it relies on that just want to eliminate this. Okay, our first try is to generate, we make the sender generates X0 and X1 in different points. So in the commit phase, he sends also X0 and X1, and then we check this as before. Some of you can see that this is not a safe choice because the sender can cheat by choosing the two elements in the same orbit, and then he can open a different bit from the receiving bit. So this doesn't work. Okay, so if the sender can cheat, we will make a proof for the fact that X0 and X1 are in different orbits. So in the phase, he commits to the bit B, and he sends X0 and X1 C, and a proof by that X0 and X1 lies by independent orbits. Also in the phase, the receiver checks, and the opening is as usual. But there is another issue here. There are no suitable techniques to produce such an interactive type construct. And this is because the language proving that series one lie in orbits is the point language. So we didn't find anything useful here. Our last try is to make is where the receiver generates series one different orbits. So it sends them to the sender. Before to the details. But we want to remove the interaction here that is so just use the previous commitment. Okay, so what we have, what we want is a way to certify the two elements lie in different orbits in the set X. And we build a framework for it. We have the following ingredients. An invariant function f going from set X into a set T, such that f is a constant on each orbit. So f of g star x is equal to f of x. For another words, the action of g does not change the equivalence. Then let T prime is a set of and we call these braces a canonical map for going from T prime to x if the following fact happens. The composition of f with these canonical maps must be the identity of T prime. So the set element braces of T when evaluated through f must return T. Okay, we want that recognize and compute the canonical map must be easy, but computing f must be hard in general. In particular, we have the following assumption. For any probabilistic adversary A, when we give the adversary an element in the orbit of braces T, it must not be able to determine T, or at least with if this stuff hold, we call this tuple gx star the invariant function in the canonical map, a group action with canonical elements. Okay, before showing you the commitment, we talk about the assumption. It's called the pseudo-normal assumption. And it's called if any probabilistic polynomial time on their series is game. We have our probability parameters, the group actions, and two elements T0 of x lying in this. Here, the challenger picks a random 2 bits, C and D, and two group elements, G and G prime. We set S as G star TC, and if B is equal to 1, it sets T as an element in the orbit of TC. Otherwise, if B is equal to 0, it sets T as an element, a random element in the orbit of T1 minus. We send this pair of element S and T, and T must guess the prime. And the adversary wins if only if B prime is equal to B. So the adversary must understand whether S and T lie or not in the same. Okay, our bit commitment works. We have our parameters given by our action with element and two elements T0 and T1 in T prime. There is a commit phase where we pick around from G and G and set our commitment to B. G's are the canonical elements of TB. In the opening, we have the sender bits, the receiver bits G and the bit. So that you can check that. We have that this commitment is computationally high under the previous assumption, and is perfect. Okay, we talked about action with canonical elements, but we missing out the instantiation tensors. Okay, we have our set given by three tensors. So even it's F3 tensor bias and there is a natural action from GL to the given by this equation. It is not needed to understand what is happening here. It's here for the main function we choose is the tensor defined as the minimal R such that the tensor can be written as the sum of R rank 1 tensors. Rank 1 tensors are tensor of this form. And it is known that first the rank is invariant under the action of G. And moreover, most importantly, F is an NPR to compute it's out in general. However, it is hard to build tensor of an array. But fortunately for small ranks, for small array, we have that the rank of this tensor by the sum of certain one tensors given from canonical elements of the basis of the space is R. So if we take T prime as a subset of set from n, the canonical map is given by this one. So the canonical elements of R is the sum of the first R tensors. We can conclude that this is a projection with canonical elements. So this is solution. Okay. So recap, we showed that non-transitivity is not a bug but a feature because our constructions heavily relies on the non-transitivity of the action. And we presented the first non-interactive commitment from the action. In the paper, you can find more on assumptions and the concept of commitments. But our commitments is applicable. This means that even two commitments on the same value, even if someone does not know the value inside them, but who produced such commitments can prove that they are commitments. In the future, it would be nice to present other perfection with elements, maybe also constructions. This we need commitments, but I think there is a larger design space. And thank you very much.
Thanks for your presentation. I want to ask whether the possibility of distribution game will be the number of copies or instead of average. Sorry, the number of copies rather than bound.
Yeah, you were asking if we can commit tomorrow. It's
no, I'm asking about the old game. Trying to in GAPR, the name is supposed to they are having the same hobbies, not the well, that depends on the number of hobbies rather than just the random guess.
maybe we can discuss. I think I didn't get
several comment in the express.
I have general questions. So it's an advantage of having to build orbit design and with something like one orbit. Okay. So what is the advantage of the unity orbit design?
size and its origin line, something like y always or other things.
Yeah, thank you for the comment. Many of these companies actually support the same. So you asked if someone can actually, here, for example, like in the first message you have key messages, and then you actually set. I think this is these are settings. Yeah, could be a possibility.
This session ends. Thanks.